Hello nerds and welcome back to another exciting lesson in Algebra 2. I know you're all I'm just perfect beginning to this video. I know you're all just itching to learn some more mathematics, so let's get right to it. Boop. We're almost finished with our chapter. We have 2 more lessons to go, this one and one more. I don't know how long those lessons are going to take to teach. Hopefully not very long at all, and here's why. Because, let me show you the Algebra 2 calendar that I have filled out already. Jokes, where the heck is this thing? Wo bist mein Calendar? What in the... There's so many papers on my table. Here it is. Here it is. Okay, so I'd like for you to see when the Chapter 3 test is. You see when that is? Right there. You see that? Anybody see a problem with that? No, that's a Tuesday. Anybody see a problem with that? Anybody see the issue with this? Yeah, you're on Thanksgiving break that week. So we have a problem here because my calendar has me going through like that. So this test was already backed up to here because I made up a day. But that's a Monday of Thanksgiving break. So we have 2 options. Teach slightly faster and get it here on this Friday before Thanksgiving break. Or don't, and you have a whole week off where you know you're not even going to think about mathematics, and then you're going to come back and have to take a test. So I think you know which one I want to do. No, God, no. We are trying to get that test on Friday of next week. So let's not monkey around too much, okay? Good news about this material. Psst. Good news about this material today, nothing new about it. You have learned all the skills that we're going to use in this lesson. This is quadratic inequalities. It's going to take the skills of graphing the quadratics, which most of you are very good at, and then it's going to combine those skills with the shading things that we were all really good at in the last chapter. Remember we were graphing the straight lines, either solid or dotted, and then we tested a point and then we shaded some stuff? It's that. So nothing new. Just taking those 2 skills and putting them together. You know what you really need to get out of this box? What you really need to get out of this is that these things are called quadratic inequalities, and you don't ever want to try to do one unless y is alone. That's it. Moving on. Okay. Here we have vertex form of a quadratic inequality. Well, vertex form is going to graph the same way as always graphed. We can see the vertex just by looking at the equation. The vertex for this quadratic is going to be at what makes the inside equal 0, 4, comma, the number to the far right, -3. 4 comma -3 is here. Right there. Okay. As before, the axis of symmetry always goes right through the vertex. So our axis of symmetry is x equals 4. The reason why I'm talking about the axis of symmetry is because these graphs are symmetric around their axis of symmetry. You see the space I left you in the notes? You might also notice that I left you a similar amount of space in the homework. That's because I expect to see some work here. And if you don't have some work here, then I'm going to have to assume that your work was not as honest as it should have been and that it came off of my answer key. The only way we can avoid that is by you showing a little bit of work. Because I don't think it's fair if I look at 2 papers and go, okay, I think Parker could have done this in his head, but I don't think Daniel could. One of them is a cheater. I'm not going to do that. What I'm going to do instead is say everybody's going to show some work because that's how I can guarantee that we're all being honest and actually learning. Okay? Okay. What kind of work am I talking about? I'm talking about plugging in another x value to get a y value so we have a coordinate. And then once we have that coordinate, we'll just reflect it over the axis of symmetry and we'll connect our dots and we're good to go. It's that amount of work. That's all I want to see. I want to see that you could plug something in and get me another coordinate. This gives us the opportunity to discuss, or at least remember, what it means when we have a fraction on the front. The denominator tells us exactly how far away from the axis of symmetry we want to go. To avoid decimals, of course. I mean, you can go as far as you want. You can stay as close as you want. You want to plug in x equals 5? Go for it. You're just going to have to graph a decimal. But if I use x equals 7, since that is 3 away from the axis of symmetry, I'm not going to have to graph a decimal. I know there's going to be a coordinate at 7 comma something. This is something I know. But I don't know the y value. We get y values by plugging in an x value. It was not a mistake that I wrote equals. I'm trying to figure out what the y value is when x is 7. So this is the work I'm looking for in your homework. 7 minus 4 is 3. 3 squared is 9. All right, well, at this point, you know how to use a calculator. A third of 9 is 3. And 3 minus 3 happens to be 0. Oh, look! I found an x-intercept, also known as a solution to the quadratic. But this is not a quadratic equation, this is a quadratic inequality. So actually, this is not one of my solutions. It's one of my x-intercepts of the quadratic. So I can just reflect it over. But what do I mean by it's not one of my solutions? You know in a minute we're going to shade something, right? Shaded points are solution points. This does not have an equal to bar. That means my quadratic is a dotted quadratic. It's not a solid line. So none of the coordinates on the graph itself are actual solutions because it doesn't say equal to. When the line is dotted, remembering from last chapter, when the line is dotted, that's the barrier to the solutions, but it is none of the actual solutions. So no equal to bar. Means dotted graph. So I'm going to connect my 3 dots, not my 3 coordinate dots, I should say, with a dashed line to the best of my ability, making a quadratic. I'll get my hand out of the way in a moment. Good enough. It's good enough. When we were in chapter 1, the way we decided where to shade was we tested a coordinate. Anybody remember what coordinate I like to test because it's easy peasy? Thomas? Oh, yeah, lots of people. 0, 0. No, it's great. 0, 0. It's easy. You could do the exact same thing here. As long as your graph doesn't go through 0, 0, use 0, 0. And just like you had before, if you get a true statement, shade where the true statement came from. If you get a false statement, shade the other place. Because there still are only 2 places. Those 2 places are in the curve or out of the curve. Those are the only 2 places. So I'm going to test 0, 0 because that's easy to do. 0 greater than 1/3 of 0 minus 4 squared minus 3. 0 minus 4 is negative 4, but you square that and you're going to get 16. Now, because I'm just checking for true or false, decimals are fine. We're just checking for true or false. 5.3 repeating minus 3 is 0.2 repeat. Wow, come on, mouth, help me here. 2.3 repeating. Is 0 greater than 2.3 repeating? No, goodness no. This is a false statement, which means 0, 0 is not shaded. And since 0, 0 is outside of the curve, nothing on the outside of the curve is shaded. That means the inside is shaded. It wasn't even a trick. We literally just tested a point because there's only 2 zones to check, in or out, and out failed, therefore in must be the correct answers. Is that concept really clear and you perfectly understand that? Because if the answer is yes, then I'm going to tell you I will never show this work again because there's a shortcut to it. Now you know that I'm not a fan of shortcuts unless I know why they're true. The shortcut only works because of what we just did. It's the same as testing 0, 0. Remember what I told you? We never try to do these unless y is alone. See how y is alone? We only try to do these when y is alone for a very specific reason. You could think of this as saying these y values of some other thing are greater than the y values that this would give me. So what I'm doing is I'm looking at these y values and I'm asking myself, where are there y values that are bigger than these? The easiest place to look is your vertex. So look directly at your vertex and then ask yourself, a y value that's bigger than this, is that going to be above this point or below this point? Above. And that's why I had to shade directly above the vertex. And that's all you ever have to wonder. Above the vertex or below the vertex. That's all that matters. Okay? For example, so you don't have to show this in your homework. You see this works. But the shortcut is, or you could just ask yourself greater than, which means above vertex, or less than, which means below vertex. For example, before I do any graphing, I should already know what this graph looks like. First of all, does it point up or down because of that negative sign? Down. Points down. It's got an equal to bar, solid or dotted? Solid. So here's what our graph is going to look like. We're going to have a downwards facing solid parabola. We see our vertex is right here. This says less than. Should I go above the vertex or below the vertex? Below. Less than means under, which means I'm going to be shaded like that. There it is. So when I'm done with this, whatever points I test, I would end up shading stuff inside the curve for this one. But it's not because of anything other than the fact that it says literally go under the curve. So if this had been an upwards facing parabola, under the curve would have been out here. It's just literally above the vertex or below the vertex. And the orientation of the parabola doesn't matter when you're asking yourself above the vertex or below the vertex. Comfortable with that idea? Yes or no? One more time. The orientation of the curve is unimportant when you're asking yourself above the vertex or below the vertex. Okay? If this had said greater than instead of less than, I would have said above the vertex and I would have shaded outside the curve. Because it's just above or below. That's all that we're asking ourselves. So this is intercept form. And just to remind you what intercept form does for us, it gives us our x-intercepts. So it's whatever makes the insides equal 0. We have x equaling -2, and we have x equaling 6 for our x-intercepts. Where, for every parabola, and lots of people can say it, can I always find the axis of symmetry? What did you say? Yeah, in between the 2 points, the middle of the graph, all of those things. The middle. The dead middle. So I would just count, and I'd see that this is 1, 2, 3, 4, 6, 7, 8. Halfway between them is 4, so 1, 2, 3, 4. X equals +2 is my axis of symmetry. The reason why we need to know where the axis of symmetry is because it's always the same x value as the vertex. So my vertex then is 2, some y value. And when we have an x, lots of people, how do I get a y? 2 people said the right answer and nobody else spoke. That's scary. We plug it in. Hey, yesterday's test. First period, 72%. Third period, 70%. Eighth period, 68%. There's a trend here. You guys got to start talking to me. Okay? Okay. Anyway, we have an x. We need to plug it in. This wasn't a mistake. I meant to write equals because I'm literally trying to figure out what the y value is when x is 2. I made a mistake in what I wrote. There. Sorry, that was supposed to be a 4. I knew I was going to write 2, though. Oh, my God. I wrote 2 again. Kill me. There. Okay. 4. 2 plus 2 is 4. And 2 minus 6 is -4. Now, the numbers -1/4 and -4 are reciprocals. What do we get when I multiply reciprocal fractions? 1. So these things actually cancel each other out. No calculator necessary. We know that my y value of my vertex is +4. Did he really just say, huh? And since we have this equal to bar, you guys have already told me that it's a solid line. like that. If you were uncomfortable with the shortcut because you still don't know why it works, you could always check the point 0, 0. 0, 0 happens to be inside the curve. Let's see what happens if I use 0. 0 plus 2 is positive. 0 minus 6 is negative. So if I multiply a negative, a positive, and a negative, I get a positive number. What's up? Yeah? No, not necessarily, because the only reason why the bottom of the fraction actually was the same distance away from the intercepts is because I made the graph's vertex so close to the x-axis. The same thing happened here. It's only because, remember I was like, oh look, a 0, it's only because I made the vertex close to the x-axis. If I had scooted it down, that essentially would have spread these things apart. If I had scooted this up, it would have spread these things apart. But yeah, so it was just so I could make it fit on this small grid, to be honest with you. But I'm happy that you asked about a pattern because I'm going to ask people to ask about patterns at the end of the lesson. That way I could try to dispel any suspicions that students have. Is that a question, Ilya?
Yeah, how did you know to kind of cancel out the -4 and divide by -?
Because these two things are reciprocal fractions. And anytime you multiply two reciprocal fractions, 2/3 times 3/2, -1/2 times -2, -1/4 times -4, when you multiply reciprocals, you always get a 1. So these two would have multiplied to be a 1, and all that's left is a 4. It just makes it so I don't have to pick up a calculator. Anyway, I was saying if we test 0, 0, we would get that 0 is less than a positive number, and 0 is less than a positive number. Therefore, 0, 0 is a shaded point, but we already knew that because we were shading under the vertex. There it is. And since this is a solid lined parabola, every coordinate on the curve is part of the solution set. That's the difference between solid and dotted. I've said that now twice. You never know if it's going to make its way into one of those which of these statements is always true kind of questions. For a test that should be a week from today. Was it subtle? Alrighty. This one is in standard form. However, I would like to change the question because I didn't want anybody to make any false assumptions. So I'm going to go ahead and write a new question, and I'm going to scribble this one out. There. Now it's a slightly different question. Just different enough. And I need to correct my notes for next year. That way it is different next year. Basically, all I did was I changed the symbols of the three terms of the quadratic. It's all I did. So let me ask you, is this quadratic going to point up as a smiley or down as a frowny? Down. Points down because there's a negative sign. Is it solid or dotted? Solid. Pointing down and solid, like this. If here's my vertex, do I shade above my vertex or below my vertex? Above, which means I'm actually shading out here, but that includes everything out here as well. So everything that will be shaded is technically above the quadratic. And I could prove that to you by talking about dropping a marble. If you drop that marble, it will hit the quadratic on its way down. That's how you know it's above it. Okay? How do I know that I shade above? Because it says greater than the quadratic. So you go to your vertex and say is greater than up or down. Greater than is up. So I have to shade up here, but if I'm shading up here, I'm shading everything above the curve. Okay, great. Axis of symmetry. When you're working with standard form, you have to find the axis of symmetry. This is the work I expect to see in the homework. I want to see you doing this. negative, your b value is negative 8, over 2 times a, your a value is negative 2, and we go from there. Negative negative gives me positive, and 8 over negative 4 is negative 2. My axis of symmetry is x equals negative 2. Standard form gives us one piece of information for free, and only one. It gives us the y-intercept. That's a trick. It's better if you understand how you find y-intercepts for any kind of graph. You just substitute x equals 0 in. Plug in x equals 0, and look what happens, though. You get 0 plus 0 plus 2. So I know this graph will cross the y-axis at positive 2. And since I know where my axis of symmetry is, I can reflect that point over to the other side as well. I have 2 coordinates. All I need now is my vertex. That's all I need. But the axis of symmetry always goes through the vertex. So I actually have the x value of my vertex already. A little bit of math to find the y value of the vertex, and we're done. Y equals, remember I'm writing equals because I'm trying to actually see what the y value is. Negative 2 times something squared minus 8 times something plus 2. And that something was x equals negative 2. Showing just a little bit of work. That's negative 8 plus 18. That's 10. Woo! Almost didn't fit on the grid, did it? It's almost like I planned it. We said it's solid. That means every single coordinate on this curve is part of the solution set. Do your best. I'm not very good at these skinny parabolas. Man, go home, parabola, you're drunk. Now above the vertex would be up here, but that's off the grid. So I'm just going to shade the parts of the grid that are still on the outside of the curve. What? He whispered my name. What? Chicken butt. Okay. What is a frog's favorite kind of shoes to wear in the summertime? Open-toed shoes. Anyway. Easy, right? Isn't this easy? Isn't this great, just taking 2 skills that we're already good at and sticking them together? Parker, question, or are you just stretching? Just stretching. Okay. Taden, you awake?
Yeah.
You sure? Oh, okay. Next. This is the only time I'm going to ask you to do something like this, and that is solve using 2 different methods. There's a reason why I'm asking you to do it in 2 different methods, though. The first thing we're going to do is we're going to graph the associated quadratic. Do you remember when we were doing solve by graphing, and I said, hey, let's graph the associated quadratic? It's the same idea. We're going to graph the associated quadratic inequality. We're going to start with that. And I'm pretty sure I didn't even have you do this in the homework. I want it in the notes so that you can have a better understanding of why what I'm going to do over here works. Because you'll have the graph to have a visual representation of why the algebra will work. Cool? Let's graph this. First of all, upwards or downwards facing quadratic? Upwards, solid or dotted? Dotted. And since it says less than, am I shading above or below? Below. So we're going to be looking for something like this setup. Okay? Yes, it's in standard form. But you know what's great about this standard form? It doesn't have a C value. And you might think that makes the question harder, but I love when standard form doesn't have a C value. Because that means that X is part of my GCF. I could solve this by factoring it. I could undistribute the 2x, and it leaves behind an x plus 4, and now it's an intercept form, which is really easy to graph. Trent, remember the other day when we were talking about the test review, and you were looking at something like this, and you were asking where the answer x equals 0 comes from? Yeah, see, it's coming up again. Look, everywhere there's an x, you say that stuff equals 0, you solve for x. So if 2x equals 0, you know x equals 0. And if x plus 4 equals 0, you know x equals negative 4, because it's what makes it equal 0. See, we're just bolstering these skills that we've just been practicing. I know my quadratic is going to cross at 0, 0, and at negative 4, 0. Oh, by the way, just reinforcing a concept. This was missing a c value, right? So what is its y-intercept then? 0. Ta-da! Okay, just reinforcing that idea. Whether or not it was an intercept form or standard form, I'm still going to have to take the x value of my axis of symmetry to plug it in, which again is x equals negative 2. Mr. M, why are they all 2 or negative 2? Because those numbers are small, that's why. It's just because the grid only goes up to the tens, so it makes it really hard to get quadratics to fit on a small square. That's the only reason why, okay? I don't want anybody to think that everything goes around a 2. It just makes it so that I can fit them on these little grids. Anyway, I literally go to Desmos and just start graphing a bunch of things and wait until it fits in a 10 by 10 by 10 by 10 grid. And I go, that's a good equation. I guess literally how I do it. I shift them up and down until they hit pretty points all over the place, and then I go, that'll work. Anyway, I know x equals negative 2, so in order to find my y value for my vertex, because right now I know my vertex is at negative 2 comma something, we have to plug in x equals negative 2. Are you getting that excited about the math that your pants are expanding? That's crazy. I mean, that's definitely what he said. I heard him. He said my pants are expanding. I mean, don't get me wrong. I love math too, but we got to draw a line somewhere, my guy. How many times a day do I tell you to save it for the locker room, right? Okay. Oops. The guy was so distracted. His swelling pants were distracting me. There we go. I'm not worried. Fire me. Don't you threaten me with a good time. All right, so my vertex is at negative 2 comma negative 8. They can't afford to fire me. I could walk around this room and slap everybody and probably still keep my job. I won't do it because I need my job. But I said I might be able to. You never know. All right, let's see. No, I'm not trying. I need this job.
It's about problem solving, right? That's about problem solving. You gotta solve that problem.
Solve what problem?
It's just, you gotta see what the probability
Nah. No, that's okay. There's some experiments that don't need to be tested, you know?
Well, this one has to
Okay, guys. All jokes aside, I know we're having fun in the classroom. All jokes aside, though, there's my graph. We've already said that I'm going to shade outside of it, correct? So look. I'm shading outside. But here's what's up. I need you to realize that I graphed something with a y value. And the original question doesn't say y is less than. It says 0 is less than. What I did was I said there is a quadratic that I could associate with it. And everything that outside of that quadratic is shading is true. But if x is the only variable, then does it make clear enough sense to you when I say that the only answers that make sense are the answers on the x-axis? Does that make sense to you? Since there was no y value? Or no? This does not have a y value, which means there are no coordinates above or below the x-axis. There is only x values. So the x values that are shaded then are my answers. Like a number line. Those are my only true answers, the ones on the x-axis. Because of the related graphs, we will never have to do that again. From now on, we solve quadratic and all polynomial inequalities using a sign diagram. And you've heard me say that terminology several times this year. So let's start solving this thing algebraically. First, it drives me nuts that the zero is on the left side. Can we all agree that this little arrow is pointing at the 0? And if I write it backwards, the little arrow still points at the 0? Nobody said no. You guys just kind of looked at me. So I'm going to go ahead and say 2x squared plus 8x is less than 0. Or greater than 0, excuse me. I said the wrong thing. But look, you see how the little arrow still points at the 0? We good here? Awesome. Going to solve it algebraically, which means solving by factoring. Could you do the quadratic formula? You could if you hate yourself. I didn't leave you enough space, though. So let's solve it by factoring. When we use sign diagrams, the vocabulary for these numbers is critical values. So anytime you have a 0 or a solution of an equation, it's called a critical value on your sign diagram. This is our sign diagram. It is a representation of the x-axis. That's all this is. We put the two numbers on there that we found to be critical. Picture not drawn to scale. Nobody cares if 0's in the dead middle. That doesn't matter. Just get the numbers on there and see that those two numbers split our number line into 3 zones. Do we see that? Okay. You will never ever need to write this. I'm only including it on the video and one time in the notes. That way you have it at least written down once. We are going to test candidate numbers, one from each zone. So from here, you pick a number to the left of -4. It doesn't matter what you choose, just pick one. So I'll test x equals -5. Then we're going to test the number between 0 and -4. It doesn't matter which one you pick, just pick one. How about -1? And then lastly, right here, any number to the right of 0. It doesn't matter what you pick, just pick one. I'll choose +1. Here's how this goes. You take the number and you plug it in for x. You don't care what the numeric value is. All you care about is the sign. Was it a positive number or a negative number? That's all you care about. Like this. I plug -5 right here. I get 2 times -5. Is that positive or negative? Negative. Good. Then there's a multiplication dot right here, right? So I have a negative number times. I put a -5 right here. -5 plus 4, is that positive or negative? Negative. So what I have here is the product of two negative numbers. What will my result be? A positive number. Great. That's a plus number, positive number, okay? Now, I do the same thing at x equals -1. 2 times -1 is negative, yeah. We've got a multiplication dot. -1 plus 4, positive or negative? Positive. The product of a negative number and a positive number is? Negative. Thank goodness Thomas is here. Come on, guys. And lastly, you're testing when x is +1, or actually any number bigger than 0, doesn't make a difference. 2 times 1, of course, is positive, and 1 plus 4, of course, is positive, and the product of two positive numbers is going to stay positive. Now here is where the sign diagram stuff becomes important. This says my quadratic is larger than 0. Is larger than 0 positive numbers or negative numbers? Because there's no equal to bar, if this was a number line, would I have open dots or closed dots on my two critical values? Because there's no equal to bar, are these dots going to be open or closed at these two numbers? Open, which is why this graph was dotted. Open dots. Positive numbers are our solutions. So everything to the left of -4 and everything to the right of 0. So our solution set is from negative infinity up to negative 4, union 0 to infinity. So why did I bother with the graph? Because I needed you to see that it would have gotten us the exact same answers. And since you were already comfortable with the shading, you were comfortable with why that part of the x-axis was shaded on both sides. But you never have to do this unless there's a y. If there's only one variable, like here, you can do this with only that kind of knowledge. This is a representation of the x-axis, and what you're describing is the kind of y values you would have gotten if you would actually plug those numbers in. That's what a sign diagram does for us. Can I move on to the last example of today? This is standard form. What's the go-to method for solving standard form? What should be your go-to method? Don't make me say an F word. I've said so many bad things already. Factoring. Oh, you're going to say the F word, factoring. Yes, okay. Factoring is your go-to method for solving quadratics that are written in standard form. The very first thing you should always hunt for, though, is a GCF, and this one has one. What is it? Negative 4. I can divide all of this by negative 4. What do I have to remember because I divided by negative? I have to change the symbol and the signs. So every one of these signs changes, but so does that. You have to say x squared plus 7x minus 8 less than or equal to 0. This quadratic also factors. What two numbers will multiply to negative 8 that will add to positive 7? What is it? Yeah, it's negative 1 and positive 8. Our critical values are what makes it equal 0. We put those critical values on a sign diagram. Picture not drawn to scale. Nobody cares the spacing between them. It's unimportant. The idea is here you have 3 zones and you check all 3 zones. First, do I put dotted or solid, open or closed dots at my critical values? Closed. Okay. People better not be packing up. I have more things to explain. You're going to want to hear it. Time to test the zones. And I'm not going to actually I'm not actually going to write anything down other than symbols. I'm going to grab a number to the left of this, like negative 9. Negative 9 plus 8, positive or negative? Negative 9 plus 8? Negative. Negative 9 minus 1? Negative. The product of two negatives? Positive. I love the number 0. It's so easy to work with. 0 plus 8 is positive. 0 minus 1 is negative. That product would result in negatives. And the last one, any number bigger than 1, like 2. 2 plus 8 is positive. 2 minus 1 is positive. The product of those two positive numbers will be positive. Now look to your quadratic. Was this looking for positive numbers or negative numbers? Negative numbers. So look here and look to see where your negatives were. They were here. Our solution set then is from negative 8 up to positive 1 inclusive. Now notice I haven't thrown the nerd sign back under the camera because I still have time to talk to you guys, and what I had to say here is going to be very, very important. Student nature, scratch that. Human nature is to look for less work. There must be patterns, shortcuts. I'm smarter than him. He only has a degree. He just wants my life to be difficult. He's not telling me the easy things. Okay. At this point in time, some of you will have started to develop what you think are patterns you can follow and shortcuts you could use that I'm simply not telling you. And I think it's very important that you start asking about them before you start doing dumb things in the homework, like trying to use slope of a quadratic to tell me where the dots are going to be. No, no. Okay? No. So please, look around. See if you think you see some patterns. Oh, a couple people. Okay, Daniel. So what he's asking me is if these symbols will automatically oscillate every single time. No, they will not. They will not automatically oscillate every single time. I'm glad you asked. That's the most important question. Please check all of the zones. It's incredibly easy for me to write an example right now where the symbols don't oscillate. So you always check, okay? Always check. Yes? Eventually, yes. It is possible for a critical value to not be a place where the sign changes. Okay? Are there times when what is going on right now? All right, never mind. Nobody wants to know the other things. Hope you do well. Good Lord.